SwayamPrabha. Digital India. Educated India.
Welcome back to our NPTEL course on Muffler Acoustics. So, this is lecture 58, probably this is the third lecture of this week, and what we are going to do today is going to have a sort of an extended session on MATLAB demonstration of the analytical mode matching method to evaluate the transmission loss performance of extended inlet and outlet muffler configuration, and also in the process do a limiting case of a concentric expansion chamber. So, that was a very basic element that we studied in the first in the very first few lectures, probably from the lecture 4 onwards. So, all that that time we studied analysis and found out nice clean analytical expressions, and then with the understanding that at higher frequencies the 3-dimensional effects are important, and then we deferred our discussion to the 3D effects until this time, until this week. So, what we are going to do is that for the first time we will consider analytical mode matching, that is the full 3D field is considered, the full modal expansion is considered in the ports as well as in the main chamber, and then using these mode expansion we will enforce the conditions of continuity of pressure and velocity, what we discussed just in the last lecture, last couple of lectures combined 56 and 57, and using the equations that we set up. So, we are going to do the MATLAB demonstration. So, before we go to the MATLAB demonstration, let me just very quickly walk you through the finally the mathematical formulation that we covered in the last class. This was the formulation that we did. Let me just go back to the few slides. So, that is we started off with the modal summation formulation in the ducts, and there was we clearly mentioned that because of the concentric nature of the location of the ports, only the axisymmetric modes they will be excited, or those are the ones that are important to be considered. The circumferential mode or the cross modes are not necessary. So, we will consider only the radial modes or the axisymmetric modes, and that is why we have written this formulation. There is no dependence on theta, that is the angular dependence, there is only dependence on radius r, okay. And we get this kind of a thing where n, of course, n is the modal particular nth radial mode or n plus 1th radial mode, and this is clearly Bessel function of order 0. So, we have this formulation in the duct A, and similar things will happen in the outlet duct, and in the chamber we had this formulation, in the annular cavity we had this, and all these things were there. They were taken from Salamet's paper, published almost more than 20 years back now, and very well cited paper, and then that kind of after that paper there were lots of such similar papers on analysis of extended inlet and outlet systems. So, what we basically do is that we enforce continuity of pressure, Pa is equal to Pc over this part as we see, and Pb is equal to Pc at the annular part, and then velocities are also matched, and then we exploit the mode orthogonality to set up a system of equations. You can refer to the last lecture, and finally what we eventually want to do is find out the reflected modal coefficients A and I, and then the modal coefficient Bn negative in the annular cavity, Cn plus, Cn minus, Dn plus and En, all these things in terms of the incident wave amplitude A naught at the extended inlet pipe. Okay. So, we would like to do that, and so all these equations were set up and they were chunks of this matrices. So, we will soon see how it is going to happen. For that, let me just walk you through the MATLAB code to begin with. So, what we do, this is the main code in which you can change a number of parameters. Just it is as simple as changing a few parameters like r underscore in, tw, r underscore in. So, this is basically the inner radius or the inlet and outlet pipe. Note that there is another important thing that I simultaneously did in the MATLAB code. I incorporated the effect of wall thickness, which has not been considered in Salamet's work, and in previous papers by Chaitanya and Munjal in applied acoustics almost about 10 years back, they did consider the wall thickness effect, but then they considered it using the full 3D formulation using some commercial package. So, this was the first time that we are considering analytical mode matching incorporating the thickness of a pipe thickness. Okay. Right now I have just set it to 0, so that we have a feel of what is going to happen. I mean, this is just a initial case, so we will gradually put it here, some non-zero value ranging from say 1 mm to 2 mm, maybe up till until about 5 mm you can have really thick pipes. So, even the small thickness of the pipe can dramatically affect the end correction, and it can influence the overall performance. Right now it has been set to 0. So, let us so I will go through these parameters, these values later, but let us understand the symbolic conventions. L is the length of the chamber, L underscore in is the length of the extensions at the inlet, L underscore out is the length of the extension at the outlet, and this is the end to end length, that is LP, that is the end. So, if you recall our discussion, so this was our so what I really mean is that if this was the formulation, let us say L underscore in is the geometric length, L underscore out is this length, and from here to here it is LP. Okay, this is LP. So, this end to end length or clearance length you can talk about. Obviously, under the limiting case, when Li this is 0 and this is also 0, okay, then you will get, and this is L. So, L is equal to LP plus this out. So, under this limiting condition, L is equal to LP, that is the overall chamber length, and we will get a concentric expansion chamber, the simplest of all muffler element, and but we can do 3D analysis without resorting to going to any commercial software, at least for such a configuration. Okay. So, this is the advantage of using this mode matching technique, and very quickly we can do that. There is obviously no finite element is involved here. So, there is no need of meshing or things like that. We can exactly evaluate in terms of the Bessel function. Okay. We can surely do that. Now, let us go to the MATLAB code very quickly, and these parameters is something that I explained. So, we evaluate the zeros or resonance frequencies or the circular chamber or the annular cavity using a parametric this file, which is somewhere which is basically sets the order of Bessel function to 0, takes in a few arguments R in R capital R underscore in wall thickness, and calculates alpha, the effective incorporating the wall thickness effective ratio of the inner pipe diameter to port diameter to the inner diameter of the chamber. Okay. And then if alpha is not 0, which is the case of annular cavity, we this function is evaluated, which is nothing but incorporating rigid wall condition on the inner pipe as well as the chamber, inner surface of the chamber. So, this is the function that is defined, and if alpha is 0, that is if you are considering R underscore, basically we are considering the modes of the full cavity or the full chamber, then this function can be defined, and this function can also be used to get the resonance frequencies of the port, that is inlet and outlet port. So, and then using root bisection method, what we do is basically we plot, we define these functions and then we plot it. This plots the function, and then using root bracketing method, it looks for a change of sign. So, these are some of the codes that you can write on your own also. Root bracketing method, that is look for a continuous function wherever the sign changes, one of the roots must be located, at least that interval S1 and S2 must have at least one root, and we ensure that these intervals are very small and none of the roots are missed or things like that. And then we evaluate the 0 using a F0 method, which is a function given in MATLAB F0. We could also evaluate this using a root bisection method, but I used root F0 and figured out that all zeros are correctly ordered, and then it basically saves it obviously the first 0 is 0 only, that is a planar wave mode in both annular cavity and this thing. So, especially the evaluation of the anything pertaining to the annular cavity where Bessel function of the second kind, Neumann function was also involved, because that function goes to infinity, singularity problem at 0. So, there you have to be careful with the 0 mode or the plane wave mode. You can just directly consider a plane wave rather than evaluating it using Bessel function. That is the only exception. So, if alpha is not 0, then you consider zeros of annular cavity, otherwise it is this thing. So, this it is stored in this file, that you get a series of zeros, that is resonance frequencies. Once you do that, it evaluates the parametric 0, and then we need to compute the number of integrals. You know, in the last class I mentioned about the number of integrals, like integral of Bessel function in the chamber, Bessel function in the chamber r square. So, this is what the orthogonal file looks like. This is the integrals file, which basically evaluates all the pertinent integrals. So, this M integral port is basically the file that calculates the orthogonal values, which is basically obtained by multiplying the Bessel functions or the mode shape functions with the square of the mode shape functions, and weighed with the weighing factor being the radius, and integrated over 0 to r underscore in or r underscore capital R underscore in, depending upon whether we have a port or a chamber. And for the annular cavity we go now from basically from r underscore in plus Tw, that is the incorporating the thickness. That is a trick we employ, that let me just explain this point a bit more carefully. So, what we do is basically incorporating the thickness of the pipe, the effective radius of the annular cavity inner radius will become r underscore in plus Tw, and the outer radius will be the radius of the chamber, that is r underscore in. So, the limits of integration for such this thing will be small r underscore in plus Tw, and the upper limit will be capital R underscore in. So, this is how we calculate the orthogonal values, and the cross modes will also be there, as we discussed in the last couple of lectures. So, this is what is calculated. Note that all these values are frequency independent. So, you just need to compute it once before starting the frequency loop. That is very important if you want to optimize the runtime of your code. Otherwise, if you calculate it every time, it is going to take a lot of time, especially if you have large number of frequency steps. So, this is like the overarching file run code, and here we have to also specify the number of modes in the port, that in the annular cavity and the one in the chamber. So, once and then these variables are declared global, because the scope of this thing is also there in the other files. So, once it is evaluated, it is these are declared now, and once they are calculated using the integrals file, and then sound speed I have taken 346.1, the one that was taken in Salamets work. This is the frequency range as usual in steps of one frequency. Now, we enter the loop. So, we just have to compute these value once, and then that will be available in the solver file. So, this is where the actual inversion of the matrix, the big matrix that I showed to you in a while, so that will happen. So, if there is no extensions, then we get the simple concentric expansion chamber case, and it basically, so let us go to this file first, solver underscore simple expansion modified. So, do not worry about the modified term just yet. So, we are left with only the solver underscore simple expansion modified. Okay. It loads the zeros of this thing. Obviously, here there is no annular cavity involved. So, whatever functions we calculated in the run file, run underscore code, the same functions now are available just by, we are not necessarily passing it. These functions are available just because these are global files. They are defined here, and the scope is also here. Now, frequency parameter, frequency response, and now this is the 2, instead of 2n plus n3 plus n2, we have 2n plus n3 only, because of the n1 number of pressure matching conditions in the inlet port and one in the outlet port, and n3 number of velocity matching conditions at the interface of the port and the chamber at the inlet, and the same at the outlet. And vector, this is defined as the loading vector, vector where, and the size is only 2n plus n1 plus n3 comma 1, and the size of this is zeros 2 n1 plus n3. This is a square matrix, this is just a vector. Okay. Now, based on all the equations that we discussed in the last class, so what we do is basically we get a chunk of matrix. So, this is, I mean, this code, all this MATLAB coding involves a lot of bookkeeping. Okay. eventually at the end of the day what we have to do is that we have to write down each of the matrix, write down each of the matching conditions and then put them in the particular go to individual rows and individual column to dump out the particular integral values. So, these are the integral values I means. So, if you for a limiting case when I is equal to 1 here, so this will become the plane wave mode, and here only diagonal entries are evaluated, and similarly this is the outlet these terms pertaining to the outlet conditions matching the pressure conditions at the outlet port. Similarly, there are large number of such terms, and here this is the contribution in the A plus term, that is the excitation plane wave excitation vector. Now, here we employ a certain trick. When k naught is less than beta by r underscore n, we take a negative, instead of taking it just j times this thing, we consider it minus j, because otherwise if we do not consider this, there might be some numerical issues of inverting the matrix, especially when very large number of modes are considered. We might MATLAB may not be able to calculate that because of machine precision. We employ this trick if this is less than, if k naught excitation frequency is less than the particular resonance frequency value, then this is negative, then we instead of just positive imaginary, we consider it negative imaginary, because you have exponential term sitting in the modal term, and then minus j into minus j, that will become exponential negative. So, there are certain tricks which you probably is best that you start coding and write your own codes, you will get to know that, and then we again dump out certain expressions these things goes in a particular row and column. So, this is the solver file, then similarly this is the velocity matching condition in the chamber, and we access particular rows and column like this. We follow this logic, and finally this is the vector where there is another contribution by the A plus term in the inlet pipe modal term, and this is where we evaluate. And finally, what we do is that once we get the fully populated coefficient matrix, only some entries are non-zero, otherwise it is 0. Once we get coefficient matrix and vector, we invert it, cof inverse of cof times vector. So, that big matrix inverse into the vector. So, that will give you the modal coefficients, then we need to convert it back, get back the positive travelling wave only for a certain mode, and so this modal cof is now passed on to the main calling function, that is your that is this function. So, we do not necessarily require cof, it is just for checking if things are fine or not. And once we get the modal coefficient, what we do is basically now evaluate the transmission loss in the transmission loss by considering only planar wave propagation in the outlet pipe. So, this is what we get. Okay. Now, we can plot it similarly when the solver modified, that is for the extend inlet, and when extensions are also involved, then what do we get? So, this is the file that we should basically open. So, just bear with me for a minute, and yeah. So, this is exactly the same, other than the fact that we need to invoke a few more integrals, 0 hollow underscore cylinder and those things. Size has increased of the coefficient matrix and vector matrix, everything else sort of remains the same, and additional matching conditions are there at the inlet and outlet. So, these are something to do with the cavities. Okay. So, all these things are there. Eventually, rather than explaining each and everything, I think it is best that you start coding and using the velocity matching conditions and following those papers, write your own codes, and whenever you are stuck up, think about it, or you can always email me in the discussion forum, and I am there to discuss. So, what we can now do is basically run this file for particular parameters. So, let us begin our thing with 0 extensions. Let us see what we get. We consider only, so this is the radius of the inlet pipe 25 mm, and this is the radius of the chamber, that is 75 mm, 150 mm is the diameter. Okay, and no extensions are considered, and instead of considering 20 modes, let us consider only 10 modes. So, make it a bit quicker and run the code. So, initially it will calculate, it is going to calculate the integral. So, now it is done. So, it flashes a message that we are doing concentric simple expansion chamber without extensions. So, what we are seeing here is live plotting of transmission loss. So, you should be really getting for the 300 length and 346 speed, you should be getting a trough here at 577 hertz, and a peak is based on again the expansion ratio. We will work out all these things, let it first compute, and after a while now the 3D effects will start to kick in. Probably I should have considered a higher frequency range. You see these domes are unequal and suddenly a collapse will happen. So, I probably have to run it again for a higher frequency range. You see these are 3D effects coming in picture. The domes are, you do not get some simple expansion chamber domes, they are now the breakdown will happen. Okay. So, I have plotted only until this time. So, what I can do, I can actually save it, save the file, it is going to take some time, and possibly run it. So, it takes about 71 seconds only, because you have pre-computed most of the integrals and employed this matching conditions. So, for a faster system it would have done a bit faster. I mean, if you have a faster system it would evaluate faster. So, now let us say we change the lower parameter and go up till 3500 hertz. Note that the justification of planar wave propagation in the inlet pipe is still okay, because the first frequency is really at high things, we will soon see. So, you see a complete collapse, we will put both the pieces together, and now we will run until 3500 hertz. So, it gets a spike. So, what we are going to do, let me close out this. Okay, this is a complete picture then. Let me save this guy. Yes. So, you see that these troughs always occur at a certain point. At 577, roughly around about that point, slightly more because of 3D effects, and you can calculate, because it is going to be something like 346.1 divided by 2 into 0.3, because C naught divided by 2L, that is the formula, right. So, it is 577 roughly, it is because of 3D effects it is showing at slightly higher things. And what is the cutoff frequency of the frequencies? Radial mode is 3.8317 and radius is your 0.075 of the chamber, is not it, and you need to multiply this thing by 346.1 and this is divided by 2 pi. So, what we get is that 2814 hertz is where the first radial mode happens in the chamber, and so let us see what are we getting in regards to this. So, what it means that before 2814 hertz this will definitely fail, and that is what is happening. The chamber is just a little after that we are getting a complete collapse of the dome and trough feature, and before it collapses it gives you a massive peak, just a bit before 2758 hertz, and then after that there is a complete collapse, and as you can see you are getting number of kind of a you will get a very spiky or a number of peaks and that kind of a characteristic. So, we can do one more interesting thing actually, we can actually increase the, and actually before we do that let us also evaluate whether we are justified in considering only plane waves in the pipe as far as transmission loss is concerned. Although all the modal coefficients are computed using modal coupling, but for calculating the transmission loss, I think we are justified here in computing taking only the first term, and that is because your here you have 0.0050 it was there na. So, 025. So, the first frequency will start at, sorry, this is not 0025, it is just 0.025, 8442 hertz, roughly 8443 hertz. So, we are much below that. So, it's perfectly fine if we consider only the first modal term for calculating the transmission loss, all right. Although for this is a subtle, this is an important point, in the pipe there will be higher order modes also, but then those will be evanescent. So, the coupling considers, when you do the analytical mode matching, the coupling between the modes in the port and the chamber are considered. So, that is what that's how these modal coefficients are evaluated. But now what we have really done is that we have just figured out the modal coefficients in the pipe, in the inlet and outlet pipe in the chamber as well, but for computing the transmission loss we are justified to consider only the planar wave term, that is the first modal term in the pipe, because we are well below the radial mode the cut on frequency. Okay. So, that is what it is. This is one point I want to tell. Now, suppose let us increase this diameter, okay, let us make it 200 or maybe 250, 5 times the expansion ratio. Let us see, and the length everything remains the same, and now let us go from 1 to 3500 hertz. Let us consider even more terms, let us say 20 terms, because more number of modes will be excited. So, this comes from experience, how do you select the modes. You should also establish convergence. So, it is what it is doing now, it is computing the pre-computing the integrals. So, okay, so we are on the track. So, you see this 3D effects will come sooner into the picture. And other thing that I want to tell is that now here the expansion ratio is 5, the expansion ratio is 5, so the area ratio is 25. So, 25 divided by 2 is 12.5, log of 12.5, 20 times log of 12.5, because 20 times log of m by 2, that is the maximum transmission loss. So, wait for a while, we will do all these hand calculations, but before that you see a much collapse in the transmission loss spectrum much before. Okay. You see a massive spike, and after that the behavior will be completely peaky, that there will be large number of peaks, and basically once the higher order modes, once you allow the higher order modes to propagate, it will be a bad thing, because then the transmission loss it will almost kill the transmission loss performance, and that is what is happening here. There will be number of domes, troughs, peaks, a mixture of that, but at least you are not, it is not like this dome and trough is very good, you can do much better, as we will soon see, but at least it is still better, this dome trough behavior is still better than this part, because essentially the muffler is transparent at once you have the higher order mode propagating for a simple expansion chamber muffler, the muffler is almost transparent. Now, let us have a look at the maximum transmission loss that you are able to get. Okay. So, what is it that you are getting? 22, and the formula says, you remember the initial lectures, m by 2. So, m is 25, because 250 by 50 or 125 by 25. So, 5, you will get 5 square is 25 and 25 by 2, you will get 21.93, and let us see what are we getting, and 22.005 is very close. Okay, and you are getting a trough exactly at 579 hertz, very close. And what about the radial frequency now? So, this becomes 125. So, 1688 is where we get the first at this frequency 1688, we definitely are at we should definitely get a peak near trough near about that 1688. So, if we just go a bit back, 1688. So, there is a modal coupling involved. So, we are definitely going down, and at trough occurs just immediately afterwards 1718, very close. It is characterized by a huge spike. Then after that, beyond this first radial mode, everything is pretty much useless. Although the values are accurate, I mean to say the muffler performance goes down after the onset of the first radial mode for a concentric expansion chamber, simple expansion chamber. Okay. But for extended inlet and outlet, we will see how these things can be further controlled. What is going to happen is that beyond the 0-1 radial mode, you still get not a very good performance, but at least it will not be as useless as this thing. So, I am going to close off this file and now do a simple case. Let us get to is perhaps we can consider this 250 or probably 150, because we have saved this file, the untitled. So, we will compare it with this case and see a dramatic improvement that it gives. Okay, the ratio, expansion ratio is only 3 or area ratio is 9. The maximum transmission loss that we get is 20 log m by 2, but with extensions, let us say half into half the extension. So, what is half of 300? This, and this is 75. Now, it is going to evaluate a different file. Okay. It is going to pre-compute a few things, and then so you will soon see at 5, instead of 577, instead of getting a trough, you will get a non-zero value there. The trough is that is lifted, but then the tuning is not there. Now, we are entering into the principle of, I am trying to do a MATLAB demonstration how do we exactly double tune the chamber. So, just by putting L by 2, now let us go to the code briefly, minimize this guy, pops away anyways. At L by 2 and at L by 4, extension length is L by 2 and the length of the extension at the outlet is L by 4. It does not help. Had it been plane wave, it would have helped. I can show you just by choosing only plane wave mode. So, plane wave mode can be chosen just by putting n1 is equal to 1, n2 is equal to 1 and n3 is equal to 1. You just consider the plane wave mode, and so then this will work, but then that will not be accurate because higher order modes are generated, and you need to consider large number of modal terms until you get a convergent solution. For our case, I guess setting 20 number of mode terms in the annular cavity and 5 terms in the mode, that should suffice. We can prove that. But what is important here to note that, assuming this is all correct, which is the results have been compared with Salamet's papers and also the ones by Chaitanya and Munjal, and there are a number of other published work and using in which experiments were done or some finite element, full 3D finite element simulation was done. So, those good comparison was obtained using the analytical mode matching using this code, which is now pretty much standard, and we are able to get performance up to 3500 hertz here, but here we get a mistuned thing. So, let us do a good comparison. I will stop, this code stops here, okay, and I will open the untitled file here, and well, this was because okay. So, do not worry about the one that happens at the later part, maybe you can kind of put it here. Okay. Now, see a dramatic improvement, and at least you are getting much better performance. So, but these troughs are still not lifted, because now let us do some fine tuning, okay, some double tuning. So, now the reason we chose L by 2 was because we wanted to ensure that the resonance frequency of the quarter wave resonator completely nullifies the first actual resonance peak. So, but then that is not happening. It is not exactly cancelling. This is the fact that you are getting a peak at 536 hertz or 535 hertz. It shows that you should have really got a peak at how many hertz? 577 or 578 hertz. The fact that you are getting a peak at 535 hertz means that the effective length of the chamber is 346.1 divided by 4 into 535, isn't it? 535, yes. Its effective length is, let me sort of multiply this by 1000 to convert to mm. So, you get 161 is effective length, but we chose only even though we chose the length to be 150, okay, but the extended inlet, that the quarter wave resonator, the inlet is behaving of as if its length is increased, acoustic length is increased to 161 mm. So, what is the difference between 161.7289 minus 150? So, here now we have the 3D effects for the first time, we have 11.72. So, that is only for this case. So, roughly, so if you have extension of the physical length to be 150 mm, half of this thing, or the chamber length, the acoustic length or the effective length is a bit more, it is about 11 mm more. So, about 11.72 divided by 150, about 7%, 7.8% more. So, basically what we do is that if we subtract this 11.7289, whatever the figure is, so if we do 1 minus this guy, or I would say, yeah, 138.2711, okay, we can put this value here, and 138.271, you can just get rid of this guy. Now, what happens to the peak due to the extensions at the outlet? So, this is 983, it should really have happened at 346.1 divided by 4 into 0.075, okay, 75 mm was the length, right. It should have happened at 1153.6 hertz, which is basically your the trough frequency roughly, okay. It did not happen, it happened much before. So, what is the effective length of this resonator then, or the resonator at the outlet? It is, what did we get, 983, 88.021 minus 75. So, we get slightly more extension length 13. So, what we do is that we kind of 75 minus 13.021, we can do that, but I would say that let us stick to let us stick to whatever extension length you get at the inlet only, and let us see if you want to avoid this thing. Now, if you choose that, you can also tune this trough. This trough will now occur at this trough, and the fourth thing is going to fail here. This you cannot prevent. So, what we are going to do is that we consider only 11.782 length, and so we will put 75 minus this 63.27. So, 63.27 length if we choose here. Before running the code, let me save this file, save here as untitled, and plot it in a different color, let us say plot in blue color. Let us see what happens. So, the good thing about analytical mode matching or these things is that it makes parametric studies very easy, okay, and otherwise you would have to mesh it again in finite elements and do a lot of post processing. For people who are very accustomed to the use of finite element software, for them it is very easy, but then this is like a proper kind of analytical work, and which is kind of implemented in a computer software, MATLAB. So, let us see what happens. Are we able to tune out the first axial resonance? The curve seems to be continuously increasing, and I hope it does not kind of give a trough at 577 hertz, which is the first axial resonance. It is probably going to completely annihilate this thing. So, it is happening here, then again it is going to come down. So, it seems that we have cancelled the first axial resonance, we have nullified the first axial resonance by tuning the length of the chamber, okay. So, and then what happens at 1153 hertz, that is the second axial resonance. So, the curve is behaving steady, nearly giving you about 20 hertz attenuation value, which is very good, and then we are exactly able to pick out and nullify that second trough, okay. There is no peak, there is no trough involved here, and then the curve is going to come down a bit, but then again you see just by tuning, providing a tuning at the inlet, this what I am trying to say is that this peak, by tuning the actual, by tuning the extension length, we are not able to nullify the first axial trough, but also the third one by the virtue of tuning this thing. By tuning this outlet extension length, we are able to nullify only the second axial resonance trough, but the fourth one we are unable to do it. We that we have already discussed in the previous lecture when we discussed the plane wave theory. So, this is the trough that you will get. So, the broadband transmission loss is limited until whatever frequency you get here. So, it is 577 times 4. So, that is roughly 2350 or whatever hertz, and then after that you are going to get a number of spikes and curves. So, this is now where you will get your 2800 hertz, 600, 700, 800, and just 2000, I think it was 2830 or something hertz, where the first radial mode starts propagating, and just before that you get a massive spike, and then things will happen. So, the basic idea is that compare the muffler performance here with this one. Amazing. We get a compare the performance of the tuned, double tuned extended and outlet muffler with that of a simple concentric expansion chamber when there was no extensions. So, just by providing a tuned extension, you can get a wonderful performance, almost a broadband attenuation for significant frequencies of interest, 2000 up to 2000 hertz, and most of the automotive noise is dominated for at low frequency 600 hertz or 1200 up to 600 hertz or 1200 hertz, basically your firing frequency and this first 3 or 4 multiples. So, what I am trying to say is that by providing very good broadband attenuation up to 2000 hertz, and it is going to give you almost 20 dB of attenuation beyond roughly 400 hertz or so until about 2000 hertz. We are covering most of the firing frequencies. We can still do better here by getting some sort of a resonator attached to the Helmholtz resonator attached to the main as a side branch to the extended and outlet muffler, but that is a separate discussion. Now, basically compare the performance with the simple expansion chamber and compare it also with the non-tuned thing. So, this peak is really cancelling out the trough, and so is the second peak cancelling out this trough. So, it is doing really good, but just by tuning we can get wonderful results. So, I will save this file also. But now comes the critical question. What is that critical question? So, no surprises to tell you, you should guess. I have set the thickness of the pipe to 0. So, what it means, let me go to the presentation. So, all this while we did not consider the thickness of this thing. Now, if we consider a finite thickness, because if you draw the cross section view, apologies for my bad drawing, that is what it is. Now, if we draw a view of this, so we get a thickness like this. So, it has, what I am trying to say is that the pipe must have certain thickness, 1 mm, 2 mm, 3 mm or 5 mm in the extreme case. Generally people do not use like 10 mm pipe or 15 mm pipe, that will be too much. So, he will stick to about 2 mm or 3 mm pipe thickness. So, even a small pipe thickness, let us say a 2 mm pipe thickness, if you do that if we make such changes in the code, let us see what are we getting exactly. So, if we these tuned values, these values are tuned based on 0 thickness. Mind you, again I am repeating, these tuned values L underscore in, that is in length of the extension, the inlet. So, geometric length is 138.27 mm only, but because of but because of higher order mode effects, the acoustic length is as if it is exactly L by 2, and that is why this troughs is getting first and second axial and third axial resonance peaks are getting nullified. But this tuning values are only for 0 thickness, I repeat. Let us consider a nominal thickness 2.5 mm, everything else remains same. So, what essentially it does is that this pipe, the inner diameter, anyways I have considered inner diameter only. So, what I mean is that this length is about or this radius is about 25 mm, and this guy, the inner radius of the chamber, outer radius can be thickness, that is not relevant. So, this is 75 mm. So, the expansion ratio is d naught by d naught, that is 75 by 25 3, and area ratio is d naught by d square, that is 9. But now focusing our attention on this thing, and what is the effective inner radius of the annular cavity? So, that is r underscore in the code plus t w, or algebraically if you want to say it is this. So, the effective radius is 25 plus 2, 27 mm. Okay. So, if we make this thing in the code, let us see what we are getting. Okay. So, let me get to the code. Now, we are in a position to run this code. So, 2.5 mm is the thickness, and I have already done this thing. Let me hit the button run. So, let us see the kind of mistuning that we get just by actually considering the finite thickness, 2.5 mm thickness, which is not all that great. I mean, that is a nominal thickness you would usually encounter in all engineering applications. So, after this pre-computing the modal integrals and the resonance frequencies and all that, we start with the live computation of transmission loss. We should be done as usual in the next couple of minutes or so. So, let us focus our attention, all these things are okay. We should really focus our attention on what happens right at the first axial resonance frequency. It will be slightly off, and at the second axial resonance frequency there will be even more noticeable deviation. So, you do get a peak, but then we will compare the performance of this thing with the tuned double tuned expansion chamber, that is the tuning at the extended inlet and outlet, but without considering the wall thickness, the results that we saved just a while back. We will compare the performance of that configuration with the present curve in just a few minutes. But we are good to discuss a couple of things here. We are getting, you see, this was not the case here. You were getting a sharp peak which was kind of very nicely annihilating the trough. Now, it is also doing its job reasonably well, but looking at this trough and looking at this peak, I am sorry, and the small trough, you would kind of, you are forced to think that there is a small amount of mistuning, all right. And so, this trough should really have been here. So, to annihilate the trough here, the peak should have been here, and this is even more noticeable for the peak and the trough here. This should have been more towards the right hand side, and this is really because the thickness effect has not really been considered in the last case. The tuning lengths were obtained without due consideration of the finite thickness, which is, like I am saying, which is very important in all practical applications. So, the end correction formula that was developed by Chaitanya and Munjal several years back, they did a bunch of, a whole lot of parametric studies in a commercial software, and to evaluate the transmission loss performance of extended inlet and outlet muffler, incorporating the wall thickness effect or the inlet and outlet pipe, and they figured out that this is what happens, and they developed an empirical relation which we can discuss just in a while. I can just present to you that expression, and now this curve is ready, and I guess I should probably change the color, because let me use another color, perhaps this thing. Okay. Well, here it is. So, you see, the blue colored curve really was much better in terms of tuning performance. This trough was nearly cancelling the peak was nearly cancelling the trough, but this is more, but in the kind of a slightly mistuned or the finite wall effect case, this mistuning is more kind of prominent, and this is even more noticeable here. In the zero wall thickness case, this peak was kind of completely annihilating the trough, but now this trough is there. So, what I will do is that I will put a legend here, I will put a legend and I will say this is also an opportunity for you guys to learn MATLAB. 2.5 mm the wall thickness, and the tuning was done for 0 wall thickness, and let us see what effect are we getting. So, it is probably saving the figure, I reckon. 0 thickness tuned, okay, and I will save this guy, say untitled 2. Now, let us get to even more extreme case where we put this as 5 mm, which is really thick pipe. Such a pipe will not kind of vibrate such big thickness pipe under flows, and let us see what we are getting. So, we should be soon be on with the computations. So, you see even more deviation, that is pretty expected. So, all these things are okay, but what we really want to see is that well, you see the transmission loss has dropped down to about 12.5 dB, okay, and you get a peak here. The peak is not sort of able to annihilate the trough. It seems there is a clear, you can clearly appreciate the mistuning, and it is even more pronounced at the second axial resonance. So, this peak and the trough are sort of not quite tuned, or they are not quite this thing, although you would see just with a small tuning you could do better. So, what I will show you ways how to tune it in incorporating the wall thickness effect as well. So, let the computations be completed, and after that I am going to, after that we really do not quite care. So, I am soon going to hit Control C to stop the computation. Seems it is not working, it wants to do its full job. So, let it compute over the entire 3000, I guess 500 hertz range, or what was it? I guess it was 3500, yes, all right, does not matter. Okay, so it is done its job, and what we are going to do, let me use some other nice color, orange color, okay, and five mm. You see massive amount of, let me save this figure first. Okay. You see clearly, if you consider the tuning length based on 0 wall thickness, and actually get the muffler manufactured or fabricated, you will have problems, because that probably not work, especially if the wall thickness is as large as 5 mm, which is still on the higher side, I agree, but even something like 3 mm, 4 mm, you will have this small mistuning problem. So, what do we do now? So, when you have finite wall thickness, so I will basically demonstrate a technique how to go about doing that. Let us consider a finite wall thickness, let us say 5 mm only, and L by 2 as usual we set it to L by 2. So, L by 2 is 150 and this is L by 4. So, this is about, note that the correction here was 11.72 mm, keep that in mind, but now in order to demonstrate the end correction we again get back this value 63.27. So, this will become 75, and instead of calculating over 3500 hertz, I would sort of stop at 2000 hertz, and okay, rest all the things are same. So, I will hit the button run and let it calculate and find out the new tuned things. Let us see what happens. So, we are basically getting a peak at we are getting a peak at something like 520-ish hertz. We will soon figure out once this code is executed completely, and let us wait for the computations to finish. So, we can as usual evaluate the effective length by noting by using the formula C naught sound speed divided by 4 times the frequency at which the peak occurs. So, that is the effective length, and from the effective length we subtract the actual geometric length to find out the net to find out the end correction length that is to be subtracted. So, that tuning can occur. So, it will be in a while. You see lot of difference. Okay, so this was the graph. So, as usual we will go to the frequency thing. So, this was our first 522 like I correctly kind of predicted. Now, this is 935, and well, we do not worry about the other one. So, 346.1 divided by 4 into 522. So, that is what it was 165.75, isn't it? 165.7567 minus 150 is the end correction length. So, 15.75. So, there is definitely a difference between 15.75 and the other guy that was 11.72. What about the other one? Other one was 346.1 and 935, isn't it? So, well, so this one was 92.54, isn't it? If you subtract 75, that is 17.54 is the length. So, how about we just consider in the one at the extended inlet only, 15.75. So, 150 minus 15.75, 150 minus 15.7567, that is your 134.24, 134.24, okay. And the other thing was 75 minus 15.7567, that is 59.2432, 59. So, let us see what are we able to get. Let us save this guy. Okay. Let us see if we are able to tune it. So, clearly one thing that we immediately figured out that 15.75 mm and 11.72. So, roughly there is 4 mm difference in case of maximum or the extreme thickness that we usually encounter in engineering applications. Especially here if you have more expansion ratio, that is 5 or 6, what I mean is that the inlet diameter can be 50 mm, outlet, the chamber diameter in the port diameter can be 50 mm, but the chamber diameter can be 250 mm or 220 mm or something like that. So, the expansion ratio is 5, 6 or something like that. So, then you will have even more effect of wall thickness, although I am not going to show you those simulations because of lack of time. Let us just focus on this thing, and couple of things to discuss before we end today's lecture. So, we get this is doing at least much better, although you would sort of imagine, you would think that this peak should have cancelled this guy. So, you are getting a peak here, and now this peak is completely annihilating the trough here, and so, and if you consider an average of 15.75 and 17 point whatever you are getting, something like 16-ish, you could do sort of even better. You could probably, this can be, you can actually take an average of this thing. So, not a problem, but this performance would be better than just L by 2 and that sort of a thing, that much I can tell you. So, this computation is done, and this, let me use another color, green color perhaps, and this is something like 5 mm. So, let me just superpose the curve here. You see what a dramatic, don't worry about these peaks are not of much value. The amount of attenuation produced at the peak is not of significant importance. The main important thing is that it should have a broadband attenuation performance. You should minimize or avoid the troughs as much as possible. So, clearly the green colored curve or the tuned thing is much better than the blue colored one or the non tuned one. Now, if we just on this curve superpose the other curve, 5 mm curve, I guess that was the curve with the tuning based on the 0 thickness thing, you see a difference. Let me just reduce the frequency range. So, you see a massive difference. So, this green colored curve is actually the tuned one, and this orangish curve is sort of mistuned, because basically what this results demonstrates is that when you considering actual applications, finite wall thickness or the extended inlet and outlet muffler should be considered to get you the actual tuned performance when you actually fabricate the muffler and do the experimental testing, whether it is able to get a broadband attenuation or not. It may so happen that you are getting a very dominant tone of the engine noise somewhere here, but then because of the peak occurring right here and you are tuned the performance, it is able to cancel that, and it is very effective, and this effectiveness will be reduced if you do not consider this. So, these are some of the important effects that I thought of highlighting here. So, I will close off all these things, and what we could do is that actually Chaitanya and Munjal in their applied acoustics paper, let me see if I have this paper readily available. So, this was the paper that I was sort of referring to, the famous paper published in applied acoustics. So, this is what they have done. They found out the end correction length by finding out the effective effective length and subtracting the effective length from the geometric length to find out the end correction, and subtracting that from the L/2 length to get the fabricated length. And so, the effective length acoustic length will be L/2 in that case. So, this is the configuration that we are talking about. Finite wall thickness was considered, and they eventually ended up with an empirical relation using which we can find out a relation between small d is the diameter of the inlet and outlet pipe, which are assumed to be equal, diameter is assumed to be equal, capital D is the diameter of the chamber, okay, and Tw is the thickness of the pipe. So, they developed a relation found using finite element simulations, the relation between non-dimensional and end corrections, that is delta A divided by D in terms of where the variables are the expansion ratio capital D by small d, and the non-dimensional thickness Tw divided by diameter of the pipe as a quadratic biquadratic function or something like that. And so, all you need to do is that these constants are there. So, this expression can also be evaluated using our analytical mode matching code or using finite element simulations, or perhaps using experiments. If you can sort of get those many muffler models fabricated. So, people rely on simulations to find out these empirical relationships, and within the within certain parameter range, for example, expansion ratio varies from 3 to maybe 2 to 6 or 7 perhaps between and the diameter can for the pipe can typically vary from 30 mm to 60 mm, a range of this thing. We can sort of get we can get a range, and wall thickness is from 1 mm to about 5 mm or whatever it is. You can also set 0 mm. We can get a very good estimate of the end corrections that is to be applied at the inlet and outlet, and using that we can tune it and get a muffler model fabricated, or if you have certain commercial mufflers which are in which these ratios are within these limits, you can very well corroborate the numerical findings or simulation findings with the experimental things, okay, and then we can easily get the end correction expression, and we can we can easily figure out whether the end correction is working or not. Mostly it will, apart from a small deviations here and there. So, this is what the formula is, and later on what we can also do, not in this course, maybe in advanced courses, advanced course on muffler acoustics, where you have this numerical and analytical techniques, we or maybe this is something like a self study. The analytical thing can also be used to analyze dual chamber muffler. Suppose if we have a limited length L, and within that we need to attenuate maximum noise. So, by incorporating maximum reflection of sound back into the system. So, what we can do, let me just sketch this guy for you. I am considering all finite wall thickness. Okay. So, you have this thing and all that. So, what we could do is the flow goes here, it comes out, and this is the length L. Original chamber was something like, it was something like this. Consider something like this. So, the idea is that divide this length into L1 part and L2 part, and again we consider just like we have done the mode matching between this section here, here and here, and found out this big matrix. Similarly, such a thing can also be applied for this dual chamber muffler, and by playing around, let the length L1, this one be small L1, this will be small L2 from here to here. Let it have finite wall thickness, T naught, and this is L3, this is L4. Okay, all this is there, and so all these things are there. Now, when we have this thing, we can do mode matching between this section and this section, this and this, this and this, this and this, and get the big matrix to finally find out all the coefficients, like the reflected wave coefficients A minus, B minus, or something like that, C plus, C minus. Now, here we will have D plus, E plus, there will be reflections back. So, you can't assume anechoic termination, E plus E minus, F plus, G plus G minus, H and I. So, here you can assume an anechoic termination, and then finally find out all these coefficients from A minus to I plus in terms of A plus. And a matrix inversion of such a system, usually one has to be careful, because sometimes it is a problematic thing when you incorporate large number of modal terms, and just by this configuration can very well be considered equivalent to, or just by once you have written the code for such a configuration using analytical mode matching, it can very well be used to analyze such kind of a configuration. Okay. And by, so this you just have to, instead of T naught, which is the wall thickness, you need to consider which is about 2 mm, 3 mm wall thickness. You need to consider a much larger value, whatever the length is. Replace T naught with say L dash, and you will the same code can be very well used to analyze this muffler configuration. So, so these analytical mode matching can help you to analyze a lot of things, especially when you have one other thing that you can do is possibly have some sort of a lining on both sides of the circular duct, and these are hybrid muffler configurations. So, these linings can really kill the high frequency noise. The moment from which the muffler starts exhibiting very peaky behavior, number of troughs and domes beyond the cut on frequency of 0-1 mode, you can actually those beyond that, the modes can really be controlled by incorporating this lining, and that can really help you. So, the higher frequencies can be completely kind of killed off. And other thing that you can also do using this mode matching is a folded resonator concept. Okay. So, that is something like this. So, there is resonator L1 here, L2 here, the length is like this, L3, L4. So, one can do a heap, lots of things with this analytical mode matching thing, provide that it is concentric circular. If it is not concentric circular, if you have an eccentric annular, something like this kind of a thing, then unfortunately this Bessel, then this can actually be used to analyze a simple expansion chamber, that kind of a thing. things like this, it can be very well used to analyze such configurations, but as has been done in Selamet's paper published several years back. But then moment you have extensions here, that probably would not be possible, at least analytically. Numerically, yes, you using numerical mode matching. So, all this will be a part of higher the next advanced level course on numerical and experimental techniques in muffler acoustics at a later stage, and we will begin with this analytical advanced techniques of mode matching, a number of advanced topics as well. So, this is what it is. And other thing, finally, before we end this lecture, we would have noticed one thing, let me just get back to the MATLAB thing, where we find out this modal coefficient, isn't it? We find out this modal coefficients when we get this. So, these modal coefficients can be plotted. This what I am trying to say is that if you consider in the cross section of the muffler, what we can do really is that plot the pressure field in this region. This was the region A, B, C, D, E. So, we can, once we know the modal coefficients, we know the exact solution. So, over R and Z plane, theta is obviously theta, there is no theta dependence, is the axisymmetric or radial problem. So, using this 2D representation, we can get the complete, we can basically plot the PR, P tilde C R Z pressure field, we can get the RMS field plotted over this distance, and then RMS field or this thing plotted here, similarly for this region, this region, this region for at a given frequency, and then we can do a frequency swipe and to see basically how these pressure contours are behaving with time. So, you will see whenever the peaks happen, very less energy will be transmitted downstream and more energy will be transmitted, and all the energy will be reflected back, and at places where you will get troughs, almost whatever power you are getting here acoustic, the pressure contours, same contours will be here. That means the muffler is nearly transparent at that frequency, not much is happening. So, all these things can give you more insight into muffler design just when you look at the pressure contours. Okay. So, with this discussion, what I will do is that I will end today's lecture, and we will meet very briefly for lecture 59, where I will just discuss some of the dissipative muffler things, although this will be covered in the later course, like I said. Once you how do you evaluate the transmission loss of a muffler using an engineering approach? You are given standard non-dimensional curves, and using that you find out certain values, and also how does the transmission loss of fully lined muffler thing, how does it look like, and so on. Okay. So, we will do all these things very shortly. Thanks.